right, folks, back here with another video looking at application of derivatives, where in this video I want to get into a topic that I probably brought up a few times in this video set for Calc 1, or I know I've mentioned in class on several occasions, and that is the topic of L'Hopital's rule. All right. A rule that is really useful for calculating limits. Limits where substitution produces indeterminate forms. L'Hopital's gives us a rule and methods that will allow us to evaluate those indeterminate results. All right, will allow us to evaluate the limits for those indeterminate results. And the rule itself involves a little bit of the derivative operation. And it'll involve some, again, application of derivatives, and we will see that. All right. I am going to break this note set up into two sets. That is my plan, 2 parts. There'll be the set here, the first part on L'Hopital's rule, where we'll go through the rule, a couple of examples, and I hope to give you a little bit of proof here. And then the second set, we're going to get into L'Hopital's methods, which is going to work for some of the other indeterminate forms we encounter where the rule does not necessarily apply directly. All right, let me bring up my notes here. Right. We are talking L'Hopital's rule, right, in this set of notes. And to open with, let's go back and consider an example. Let's consider back at the beginning of the semester when we introduced indeterminate forms. To introduce the technique known as squeeze theorem, we set up, using a little bit of geometry, the calculation for the limit as x approaches 0 for the sine of x divided by x using the squeeze theorem. And we had shown that this limit was equal to 1 through a rather rigorous and rather implicit setup. This result, right, was developed for this limit, where with L'Hopital's rule in hand, we can actually calculate this limit rather quickly, right? It's a quick, easily obtained result. It doesn't require a lot of rigor, right? It will involve primarily finding the derivative of the numerator and denominator for this rational form, which is not difficult at all. The derivative for sine is cosine, and the derivative for x is 1. That's about as rigorous as it gets, other than having to evaluate the limit in each step of the rule. All right? Let's look at the rule. Here's L'Hopital's rule. And L'Hopital's rule says, let's assume as x approaches a for f of x divided by g of x results in either the indeterminate forms plus or minus infinity or 0 divided by 0. Then what is true is that as x approaches a for the format f of x divided by g of x, this is equal to the limit as x approaches a for what is going to be f prime of x divided by g prime of x. Now this is all, I should put in some conditions here. This is all provided f prime and g prime are continuous at that value of x equal to a. we can use this technique. And you'll notice what it says is that our limit for this rational form f of x over g of x that produces either infinity over infinity or 0 over 0 through substitution we add from substitution, right? What we're able to do then is consider the limit, right, as x approaches a, the same limit application now applied to what's going to be the derivative of the numerator divided by the derivative of the denominator. F prime of x divided by g prime of x. Right? We're able to evaluate the limit for this ratio of f of x divided by g of x by looking at the limit for the ratio formed by their derivatives, their rates of change. As I said, all you're going to need to really know how to have to do is to find the derivatives for the numerator and denominator of the rational form in your limit. If we go back and consider that case that we proved using squeeze theorem earlier, right? In that case, through substitution, it does produce the indeterminate form 0 over 0. Where L'Hopital's rule then states that if we want to know the limit as x approaches 0 for sine x divided by x, this would then be the limit as x approaches 0 for the derivative of the numerator, the derivative of sine x, divided by the derivative of the denominator, the derivative of x. And as we said, these two derivatives are not tricky to find. The derivative of sine is cosine, the derivative of x is 1. And if we bring that result into view here, we will note that that does simplify from the cosine of x over 1 into simply the cosine of x, where the limit as x approaches 0 for the cosine of x can be evaluated through substitution. When we plug in 0 into the cosine of x, this does end up equaling the cosine of 0, which is equivalent to 1 in value. The noted value of the limit that we showed earlier this semester using a little geometric setup and the squeeze theorem. All right, that is L'Hopital's rule. We came upon this result of 1 for this limit pretty quickly, right? Pretty easily just using our rule of derivatives. All right. And thus, from L'Hopital's rule, we can say the limit as x approaches 0 for sine x over x must be equal to 1 in value. All right. Next, let's consider proving the rule. All right. Let's consider proving L'Hopital's rule for the case of the indeterminate form of 0 over 0. Right? Where we want to prove the limit as x approaches a for f of x over g of x must be equal to the limit as x approaches a for f prime of x divided by g prime of x. And we must prove this when it is the case that f of a would be equal to g at a, which would be equal to 0, right? Because we note through substitution that if we attempt substitution here, this will produce f of a over g of a through substitution. And if we're going to encounter the indeterminate form 0 over 0, that's going to imply these two results, f of a and g of a, must be equal to each other and equal to the value of 0. Right? As we noted also above in the conditions for the rule, f prime and g prime must be continuous at x equal to a, and in the end, g prime of a is not allowed to be equal to the value of 0. G prime of a equal to 0 will end up yielding an undefined result in the end. All right. Well, under these assumptions, since f of a and g of a are both equal to 0, subtracting them in the numerator and denominators of our limits argument has no effect, right? That's like subtracting 0 in the numerator and subtracting 0 in the denominator, which has 0 effect on the numerator and denominator. Right? Bad pun there. Right? With 0 effect, we can then take this argument here and write it into this argument seen down here by multiplying both the numerator and denominator by the quantity 1 over x minus a. The quantity 1 over x minus a over itself is actually just equal to 1. So multiplying this quantity by 1, as we note, has no effect. So multiplying here by 1, we can do that using this format, 1 over x minus a divided by 1 over x minus a. Where that 1 over x minus a in this numerator can multiply by the numerator of f of x minus f of a, or over g of x minus g of a. And the 1 over x minus a in the denominator of this factor can multiply itself into the denominator of this factor, producing this result seen here in our argument. This result in the numerator over this result in the denominator. Since a limit will distribute itself across numerators and denominators, we can then go on to say that that limit as x approaches a for f of x equal to g of x must be this limit that we see in the numerator divided by this limit that we see in our denominator. Where those two limits might look familiar. When we had talked derivatives as rates of change, you might recognize those as average rate of change calculations with a limit applied to them. Where back in our case for for derivatives as rates of change, letting h equal the quantity x minus a, this quantity x minus a seen down here in the denominator, that does imply that the x can be rewritten as a plus h, seen here in the numerator of f of x minus f of a, and in the numerator here of g of x minus g of a. We're able to replace that x with a plus h. So if we go into these limits here, and we make those replacements, we should see something that is even more recognizable, hopefully, to us. This limit here is x approaches a for f at a plus h minus f of a divided by h. All divided by this limit as x approaches a for g at a plus h minus g of a divided by h. Where by definition of the derivative, we should recognize the numerator is f prime of a, and the denominator is the quantity g prime of a. And since f prime of a and g prime have to be continuous at a, what that implies is that these results for f prime of a and g prime of a must then be equal to the limit as x approaches a for f prime of x. Remember, that's what it means to be continuous at a point. To be continuous at a, f prime, for f prime, the limit as x approaches a for f prime of x must equal f prime at a. And a similar result can be stated for g prime of a in the denominator. So in the end, we end up with the limit as x approaches a for f prime of x divided by g prime of x, equaling the limit as x approaches a for f of x divided by g of x. All right. End proof. All right. That is the end proof there, folks. We have shown, right, thus, I should probably say here. Thus, it has been shown under the given assumptions, the limit as x approaches a for f of x divided by function g of x must equal the limit as x approaches a for what's going to be f prime of x divided by g prime at x. Right. We have shown and proven this result. All right. Now, one thing I will go back and note, we have only proven it technically, explicitly, for the case where we produce this indeterminate form 0 over 0, where f of a is equal to g of a, which equals the value of 0. One thing we ought to note, though, for the case of infinity over infinity, plus or minus, infinity over infinity can be thought of as being equivalent to 1 over infinity divided by 1 over infinity. This infinity in the numerator, in a sense, can be moved to the denominator if we write it as its reciprocal. And this infinity in the denominator can be moved to the numerator if we write it as its reciprocal. And what we see for the behavior of infinity over infinity, or 1 over infinity divided by 1 over infinity, its equivalent, is that is actually approaching 0 over 0 in value. It is approaching this indeterminate form 0 over 0, implying a similar result for L'Hopital's rule would be also expected in this case. Since infinity over infinity approaches 0 over 0 in value, they are, in a sense, equivalent in the context of a limit. And since they are equivalent in the context of a limit, the above proof for the case of 0 over 0 is also true for the case of infinity over infinity. That's the proof of L'Hopital's rule. Let's look at another quick example. And we'll come back in another video and look at some methods. But here's another limit that we proved earlier in our notes, right, with a little bit of squeeze theorem. And that was the limit as x approaches 0 for e to the x minus 1 divided by e to the x. Through substitution, we should be able to see that that does equal 0 over 0. Right. We get 1 minus 1 in the numerator, which produces 0, and substituting in 0 into the denominator also produces the result of 0 in the denominator. So by L'Hopital's rule, the limit as x approaches 0 for e to the x minus 1 divided by x must just be the limit as x approaches 0 for the derivative of the numerator, e to the x minus 1, divided by the derivative of the denominator, the derivative with respect to x for just x. The derivative of e to the x minus 1, though, is just e to the x, and as we've seen, the derivative with respect to x is just 1. So this ends up becoming, through L'Hopital's rule, the limit as x approaches 0 for e to the x divided by 1, which does simplify to the limit as x approaches 0 for e to the x, where through substitution is just equal to e raised to the 0 power, which is equivalent to the result of 1. Right? The result that we proved earlier for this statement using a little squeeze theorem. That's L'Hopital's rule, folks. If substitution produces the format 0 over 0 or infinity over infinity, the limit that produces that result through substitution can be rewritten, right, as a similar limit argument where you want the limit as x approaches a for the derivative of the numerator divided by the derivative of the denominator. L'Hopital's rule. All right. Here's the rule applied in this example that we showed earlier in the notes using a little bit of squeeze theorem. And the rule is a lot easier to apply than setting up the squeeze theorem. All right. We looked at its proof, which does rely a little bit on the definition of the derivative and algebraic manipulation of our argument for the limit underneath our assumptions. This work here, all of it really. Right. We presented the rule, and we had shown the result here also for the case of sine x divided by x. A similar result that we proved earlier in our notes. All right. This is L'Hopital's rule, folks. I will point out, keep in mind, there are other indeterminate forms, right? Infinity minus infinity, 0 times infinity, 1 to the infinite power, 0 to the 0 power, and infinity to the 0 power are other indeterminate forms that we can also encounter through substitution method and limits evaluation. Where in those cases, we're going to use some of what we call L'Hopital's methods. All right? And that's where we're heading next, is to start to look at the methods applied in those cases. Now, those methods are going to bring about more use of L'Hopital's rule. Some of those methods, or all those methods, I should be careful there, some of those methods, actually it's all of them, all of those methods are going to require us rewriting our arguments so that L'Hopital's rule becomes applicable. And in these follow-up methods here that we're going to see for these other indeterminate forms, we are going to be applying the rule in those cases also. All right, the rule is going to incorporate itself into the methods. All right, so that is the next video I have for you, folks. But I will end this one here, and I will come back looking at L'Hopital's methods. And we'll pick back up then, folks. So I will see you in the next one.